Okay, so in the last video we introduced the notion of molecular orbitals and molecular orbital theory, and that's a video you might need to watch a couple of times. It's a lot of sophisticated ideas, but the more we work with this, I think the more intuitive it will start to feel for you. And so in this next video I'm going to work through some slightly more complicated examples, and as I do, you'll see more of the principles that I outlined on the last video in action. I think they'll make more sense to you when you see them as examples. So we're going to move next to talking about describing the molecular orbitals of the second row diatoms. So this will be really beryllium 2, boron 2, all the way up to fluorine 2. And so let's maybe start today with the example of oxygen. This is one of my favorite molecules. And of course, with our thinking about fuels, this is really an essential component of many, many fuel reactions. Okay, so we're going to follow the same rules. We're going to make a molecular orbital diagram for oxygen. So you know that we start by putting the atoms on the side, and then we put the molecule in the middle. And now we have to line up our atomic orbitals that we have, and we're going to add and subtract them to make molecular orbitals. I didn't emphasize this in the last video, but we're only going to be working with valence electrons. You've seen that before, that the core electrons, because they're not very effectively shielded, they feel a very large effective nuclear charge, and so they're held very close to the nucleus. They don't effectively overlap, and they don't form chemical bonds. So the bonding is just between the valence electrons in atoms. So in oxygen, we have a 2s atomic orbitals, and we also have 2p atomic orbitals. And we sort of know what these look like. We do know what these look like. Now, for the first time, when we think about the p orbitals, we're going to begin to think about the differences between the px, py, and pz. And the reason for that is that now when we're bringing two atoms together, space is not the same in all directions. If you're just thinking about an isolated atom, it is. But now there's going to be a distinct difference to the axis that connects the two atoms versus the ones that are perpendicular to that. So for the purposes of bonding, the p orbital that lies along, so again, we're bringing these two oxygen atoms together. By convention, the axis that they connect on is called the z-axis. We just pick an axis, and it's that. So the pz orbital is going to be different for us in making these molecular orbitals than the px, the py, or the pz. And so we'll draw that one like this to make it clear that that's the axis we're going to be bringing the atoms together along. The other thing that I didn't emphasize when we were talking about atomic orbitals, because it didn't really matter much, but it will matter now as we start to use them to make molecular orbitals, is that while the wave function for the electron in an atom does not have any physical significance, when we add and subtract atomic orbitals, we're in fact going back and adding and subtracting the wave functions, and then taking the absolute value of the wave function and squaring it to get our orbitals. And so because we're doing that, we actually have to remember something about the phase of the wave function, which we didn't need in thinking about orbitals. And so by phase, I mean, if this is a wave, and there's my axis, this would be the plus phase, and this would be the minus phase. If I take that wave function and square it, I get something that's positive every place, and since this is my orbital, that's really all we've thought about now. But when we're thinking about adding and subtracting atomic orbitals, we're going to remember that the p orbitals themselves had a positive and a negative phase to the wave function, so something like that. Again, it didn't matter for talking about atoms, but it is going to matter now when we add and subtract them. So we have our pz, we're going to have a px, and a py, and it will turn out that what we call px and what we call py isn't going to matter, but we just keep them all there, okay? So now we have our ingredients to make our molecular orbital with. So we'll draw a line here so I can keep this nice and neat. So again, on this side of the diagram, I have atoms. Those are the ingredients. In the center, I'm going to make the molecule. And again, just as we've seen throughout this semester, or at least throughout this section, on the y-axis, I'm plotting energy. The lower in energy, the more stable. And at this level, and really for a lot of chemistry, we're going to be more interested in relative energies than we are going to be exact energies. Computational methods are powerful enough today that we can use them to calculate the energies of electrons in molecules, and you'll do that if you go on in chemistry. But the sort of conceptual information that really helps you predict reactivity of molecules day in and day out does not depend as much on having quantitative numbers here, but rather a qualitative sense of the ways in which the energy of electrons are lowered, are stabilized, when atoms join up to become molecules. So if you go back to your rules, and you should probably, if you don't have them now, you should take a moment and write down the rules for forming molecular orbitals from atomic orbitals. So you take a moment and do that. If you look at those, we know that the first thing is we're going to add and subtract atomic orbitals to make molecular orbitals. At the end of the video, we should have the number of atomic orbitals equal to the number of molecular orbitals. So in this case, we have a total of 8 atomic orbitals. When we're done, we should have 8 molecular orbitals here. We'll only be adding and subtracting atomic orbitals of the same symmetry, and we're going to only add and subtract atomic orbitals that are close to each other in energy. And every time we add an orbital, add two orbitals, we'll make a bonding molecular orbital that will be lower in energy than the atomic orbitals it came from. And we'll then have to subtract the atomic orbitals as well to make an anti-bonding orbital that will be higher in energy than the atomic orbitals that it came from. Okay, so let's get started. So we're looking at our valence electrons. Starting here, we have 2s. This is going to be exactly like what we saw before for hydrogen. So we're going to add those together. We're going to make a bonding molecular orbital that looks pretty much like what it did before. So this will be a sigma bonding molecular orbital. It will be from 2s plus 2s, and that will be lower in energy than the atomic orbitals that it came from. And then we're going to make an anti-bonding molecular orbital, which will look like that, which will be 2s minus 2s, so this will be a sigma anti-bonding orbital, and that will be higher in energy than the atomic orbitals that it came from. Okay, this looks good. So now we get to these p orbitals. So what do we do with p orbitals? Now we sort of, for the first time, really encounter this idea of what does it mean for orbitals to have the same symmetry. So let's look first at what would happen if we added the pz plus pz. So we're going to add these together. And again, this would be as though we were doing, I'm going to add this, and I'm going to add that to something that looks like this. And so when I do it, these two parts of the wave function add constructively, and that means that when we add them together, the total wave function, the total amplitude of the wave function will increase. This is what we call constructive interference. This is an idea that might be familiar to you from physics. If not, it just kind of, I think it makes sense intuitively that if we overlap two things and they add, the amplitude gets bigger, and then the other parts, the negative parts, doesn't really have much effect here. So if we add the pz and the pz, we can make an overall molecular orbital where we have a lot of electron density in the middle, And again, if you think back to what we've been saying for a couple of weeks, this is the region between the two nuclei, and so it will be stabilizing for electrons to be in that region. And then we have these other two smaller lobes that point away from the region of electron density. So again, we've taken these two shapes and we've kind of stacked them on top of each other. It really is as though I took this and then I put this on top of it. And in this region here, where they overlap, maybe I should do that in a slightly more contrasting color, they add constructively to make a big region of electron density. But now we have to ask ourselves, so this is a bonding molecular orbital. It still, however, has sigma symmetry. If we rotate it around that internuclear axis, it still looks the same. If I rotated it by 180 degrees and you weren't watching, when you came back, here, I'll do it. Shut your eyes, rotate it by 180 degrees, it still looks the same. So that is the characteristic of a molecular orbital that has sigma symmetry. So this is a sigma bonding molecular orbital. And just to distinguish it from the one we made with the 2s plus the 2s, we'll call it a pz plus pz. So this is going to be lower in energy. This is going to be, it's going to look like this. Again, this is just me redrawing that. And it will be sigma bonding pz plus pz. And then I have to do the anti-bonding combination as well. So this was my bonding combination. In the anti-bonding combination, it's like I'm going to be adding the negative. And so in this, I'm going to have lots of nodes. These are nodes. This indicates a higher energy orbital structure. And when I add this together, we're going to end up having a lot of electron density in the region away from the nuclei and less electron density in the region between the two nuclei, making this a higher energy molecular orbital. It still, however, has sigma symmetry. If I rotate it around that internuclear axis, it looks unchanged. So this is a sigma anti-bonding orbital, but it's pz minus pz. And so in our diagram, that will be higher in energy than the atomic orbitals that it was made from. Sigma anti-bonding pz minus pz. And again, we can draw that like this. And you just need to get used to the idea that the more nodes, the more shaded, the more times the shading changes, the higher in energy. Okay, we're making great progress. We just have to consider the other two kinds of p orbitals. So what happens now if I add px and px? So when we take and add two px orbitals, again, there's no electron density right along the internuclear axis, but we're still going to have a lot of electron density above and below the internuclear axis. And again, that's better than nothing because we still have these positive charges here. So it's not really as great as the sigma bonding. I shouldn't have shaded this. But we still are been bringing together these two atomic orbitals. We're making a bonding molecular orbital that is lower in energy than the atomic orbitals from which it was made from. But now the symmetry is different. Now if I rotate this, or you can maybe see it a little better here, if I rotate this by 180 degrees around that internuclear axis, and again, shut your eyes, and then you will come back in 30 seconds. Okay, you can look. So I rotated it by 180 degrees, and you can now tell it looks different. I know this is just the sign of the wave function, and ultimately that doesn't have a physical significance, but when we're thinking about the construction of molecular orbitals, it does. And so molecular orbitals with this kind of symmetry, where it's the exact opposite when you rotate it by 180 degrees around the internuclear axis, These have the name pi. That's just what we call them. So this is a pi bonding molecular orbital. And the alternative so this was px plus px or py plus py, px minus px, or py minus py will look like this, where we have lots of nodes, but this too still looks exactly the opposite when I rotate it by 180 degrees. So here we have our pi antibonding orbital. And again, these orbitals in general are a little less beneficial than some of these sigma bonding molecular orbitals we've made. So in general, the energy of the bonding molecular orbital is not as stabilized relative to the atomic orbitals it came from. So this is our pi bonding molecular orbitals. And these look like this, just in the two different axes. And then we have if the good isn't as good, the bad isn't as bad. So there are our pi antibonding orbitals. And we will spend time in class drawing these as well. So and you'll also have examples in your text. Okay, we're almost done. I know this is looking like a lot of work, but I promise you it's going to be worth it. Let's just check ourselves. We had 8 atomic orbitals. Now we have 1, 2, 3, 4, 5, 6, 7, 8 molecular orbitals. Check. We added and subtracted atomic orbitals of the same symmetry. You saw that here. Check. We only added and subtracted atomic orbitals when they were close in energy, and in fact, since we're working with what we call a homonuclear diatomic molecule, they were exactly the same in energy. Check. Our bonding molecular orbitals were always lower in energy than the atomic orbitals that they came from, and our antibonding orbitals were always higher in energy than the atomic orbitals that they came from. Check. Okay, so the last thing is to put electrons in. And oxygen, you know, has 1, 2, 3, 4, 5, 6 valence electrons. We're going to, again, use the Aufbau principle. So we're going to fill the lowest energy orbitals first. So we've got a total now of 12 electrons to put in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we're done. So let's calculate our bond order. So our bond order will be the number of electrons in bonding molecular orbitals. So that will be 2, 4, 6, 8. Minus the number of electrons in anti-bonding orbitals. That will be 2, 4 divided by 2. So we have a bond order of 2, which is what we would have thought from our Lewis dot structure. But as we'll discuss in class, we'll work a number of problems with this. There is a lot more information in this molecular orbital diagram than there is in our Lewis dot structures. And there's a lot more information that allows us to understand how oxygen reacts in this picture than we have here. So this picture ends up being really powerful for thinking about things like the fact that we know that oxygen, molecular oxygen, is a molecule that has unpaired electrons. You would never get that from the Lewis dot structure, and yet it's observably true. And that kind of information is really explained well by the molecular orbital picture. So we're going to practice with this. We're going to do a couple of examples in class looking at molecular orbital structures and how it affects bond order and ultimately how this relates to the strength of the chemical bonds. We'll let this be enough for right now, and in a little bit we'll come back and talk about a few more examples of diatomic molecules, as well as what happens when we start to make molecular orbitals from different atoms.